So previously we have gone through a review of semaphores. In doing so, we also looked at some pseudocode examples, and our discussion was based on section 14.2 of the book Unix Systems Programming. And then afterwards we moved towards understanding how semaphores are available in POSIX conforming operating systems. Our focus is on Linux. So after going through an introduction to that interface, the name of the functions, and how to use them, we will now see an actual example. Okay, so previously we have seen an implementation of the producer-consumer problem, and this was done using shared memory. And over there, we also saw that we had no synchronization facility available. Shared memory does not provide any such mechanism on its own. So over there, the coordination between producer and consumer processes was done using busy waiting. And we all know that busy waiting is never a good idea. What we will see now is how busy waiting can be eliminated by employing POSIX named semaphores. Right, so this figure shows producer-consumer example. We have two processes, one producer and one consumer. And in the center, you see the shared memory. Inside this shared memory, we have two items, a data and a flag. The workflow here starts from the left, where the user is prompted by the producer process to enter some text. This text is captured by the producer process, which will place it in the data field inside the shared memory. After it will raise the flag value from 0 to 1. Meanwhile, the consumer process is stuck in a busy waiting loop, and when the flag value is raised from 0 to 1, it comes out of its busy waiting and it is going to retrieve the data item. After retrieving the data item, it is going to reset the flag down to 0 and will display the item on screen as well. So in essence, this is an implementation of the producer-consumer problem with a buffer size of 1. Because shared memory itself does not provide any synchronization facilities, the synchronization between the two processes here is done with busy. So here we have the listed POSIX named semaphore functions. We will use both variants of SemOpen, and the difference is in the number of parameters which are accepted by the two variants. Next, we have the two standard operations for the semaphore, semWait and semPost. In some books, semPost is written as semSignal. When a process is done using a semaphore, it can close the semaphore on its side using semClose. This does not delete the semaphore, it only makes it closed from one process. The semaphore is still present in the system. To finally delete a semaphore, a process can call semunlink. This is going to delete the semaphore from the system and also remove the file name entry corresponding to the semaphore. To compile the programs, you will have to use the commands as shown over here. In some cases, there might be variations. Please consult the documentation of your Linux distribution. Right, so we have the common header file shown over here, where we have a structure defined. This structure is going to be the layout of contents of our shared memory. You would notice that it contains one character array, which is our data, and it does not contain any flag this time, because when we use semaphores we don't need any flags for synchronization. Also, you will notice that two file names are defined using macros. Next, we have the core of the consumer process, and this is the list of header files. You will notice that our custom made header file is also used. Continuing with the code of the consumer process, you would see that we have two pointers declared of semaphore type, and these are going to be used to store the return value of SemOpen. You will notice that semopen is called twice along with the o_create flag. The first call is going to create the empty semaphore. This is going to be the file name as the first parameter, and the initial value of this semaphore is going to be 1. The second semopen call is going to create the semaphore which is fulls, and the initial value of this semaphore is going to be 0. The return value of both semopen calls is inspected for error, and also we give a seed value to the random number generator.